Hello, my name is Michal Przewozniczek from Wrocław University of Science and Technology, and I will present our work considering the direct linkage discovery with empirical linkage learning techniques. I will start from some simple example of why problem decomposition and linkage learning may be helpful in optimization. Then I will briefly describe some statistical-based linkage learning techniques, SLL, and methods which are using it. Finally, I will present an empirical linkage learning, which is a recent proposition and significantly different than statistical-based techniques. Then I will present the paper objectives and the new empirical linkage learning technique, which we are proposing, namely the Direct Linkage Empirical Discovery, DLED. I will show you why we propose it and how it works. And then I'll, of course, present the results and summarize the presentation. So let's consider the max-free-sat problem. The max-free-sat problem is built from n logical variables, and these variables are grouped in three-element clauses. Our objective is to satisfy as many clauses as we can. So let's consider such solution. We have 4 variables and 4 clauses, and for such solution we have C1 and C2 clauses satisfied. So what do we want? We want to satisfy C3 and C4. What we can do, we can set the value of third variable to 1. However, if we do this, then we will lose the first clause. It will not be satisfied anymore. So what we need to do is we need to set the third variable to 1 and the second variable to 0. And if we do this together, then we'll get the solution which satisfies all 4 variables. So the question is, the variables in a single clause, are they dependent? It seems reasonable to state that, yeah, and they should be exchanged together. And then if you do this, if you exchange dependent genes together, you may expect that your GA optimizer will work more effectively. Statistical-based linkage learning. The general idea is that, okay, we have the genetic algorithm. The GAs have the selection pressure, so we have the population which is under this pressure. And in general, in the subsequent iterations of GA, we expect that the individuals will tend to converge to better solutions. So what we can do is we can count the frequencies of pairs of gene values, which are represented by our population. If we have it, then we can compute the entropy. And then we can create the matrix of gene dependencies, so-called the DSM matrix, and we can use this information. It's typically used during the mixing operations, so the crossover-like. And then we can exchange only those genes which are dependent on each other. And the DSM-based linkage learning may be used, the statistical-based linkage learning may be used for many different search spaces, for discrete, binary, and non-binary search spaces, for the permutation-based problems, and for the continuous search spaces as well. The SLL using EAs are, for instance, the LTGA, which is the closest to the genetic algorithm idea, the parameterless population pyramid, P3, and DSMGA2. Now, the P3 is, of course, parameterless. However, linkage to LTGA requires one parameter, which is the population size. And it was improved and it created the LT-GOMIA, which is the multi-population version of LTGA, which is parameterless. The similar operation was done for DSMGA2, and we have population sizing DSMGA2, which is parameterless as well. Now, the question is how effective this kind of methods may be. We can consider the key shortest Steiner tree search problem, and we in this paper we have considered the P3, LTGA, and DSMGA2 runs in 1 minute. They were given only 1 minute of computation, and they were compared with Cplex, which was supported with 2 hours of computations. So here we have some results. The first 3 blocks here and here, these are the linkage learning methods, and they significantly outperform all other competing methods. And here, this last block here is the Cplex, but with runs which were supported 2 hours of computation time. And you may see that these results here are, first of all, very well, quite similar in quality to the simplex with 2 hours runs, and P3 and LTGA actually are able to outperform with 1 or 3 minute runs the simplex, which is given 2 hours of computation time. So this result seems quite convincing, at least for me. Empirical linkage learning. Well, for some problems, the DSM-based linkage learning techniques are unable to precisely decompose the problem structure. So the new linkage learning technique, or actually the group of techniques, was proposed recently. They use a different idea than the statistics, the DSM-based linkage learning, and they successfully decompose the DSM hard problems. Now, how it works? Let's consider an individual. We can say it's binary encoded, but this kind of idea may be applied to other search spaces as well. In this individual, we can make a small perturbation. We exchange the value of the nth gene, and we flip the gene value here. What else we can do? We can use a greedy optimization algorithm to optimize the genotype of the original individual, and we can use exactly the same algorithm to optimize the perturb individual. Now we can compare the results of this optimization. Now, if these two genotypes differ, then all the differences are caused by this perturbation. If all these differences are caused by the perturbation of this single gene, then we can say that all these genes are dependent. And such a piece of information is called a linkage scrap, and linkage scrap is an information about the group of genes which are dependent on each other. Now, this technique is called the linkage learning based on local optimization, 3LO, and it's empirical linkage learning because we do not use any predictions or statistical measures. We just check which genes are dependent. The linkage scrap is a piece of information, a set of genes which are dependent. And what is important is that we have proven that 3LO never reports a false linkage. The false linkage takes place when two independent genes are marked as dependent by your problem decomposition technique. And we, of course, support the appropriate proof of this. However, of course, 3LO may sometimes miss to detect some linkage, which takes place when two genes which are dependent are overlooked. The dependency is overlooked by the linkage learning technique. Now, the main features of 3LO is that it's precise because it never reports the false linkage. However, its drawback is that it's computationally expensive. The other thing is that, fortunately, it's applicable to any discrete search space, which is quite a nice feature. Now, how to use it? We cannot apply it directly to SLL using EAs like P3 or LTGOMIA because they update their linkage frequently, and 3LO is very expensive, so it is not applicable to these methods, and we had to propose a new EA to utilize 3LO. Now, let's consider the direct linkage issue, which we present in the paper. Let's consider the problem built from 3 blocks, but these blocks are partially overlapping. So the first block is defined on genes 1, 4, the blue block is on 4, 7, and the green block is defined on genes 7, 8, 9, and 10. So the blue and the red block have the 4th gene in common, the blue and the green block has the 7th gene in common. Now, the ideal decomposition of such a problem is shown here. So we want to know that gene number 1 is directly dependent on genes 2, 3, and 4, and nothing more. And gene number 4 is directly dependent on genes number 1, 2, and 3, because it's a part of the red block, and genes 5, 6, and 7, because it's a part of the blue block. So if we get only direct gene dependencies, then we will be able to better model the structure of overlapping problems. And the question is, can 3LO support such linkage? Can 3LO support only the direct linkage? Let's check it. To check this, we will use the bmodel order 4 function. here we have the unitation. The unitation is the number of ones in the genotype. If we have only zeros or only ones, the value of the function is optimal. If unitation is 2, we have the suboptimal values. So the optimal genotypes are only zeros, only ones, and the local optima is when we have 2 zeros and 2 ones, which are shown here. Now, let's consider such solution to this problem. If we optimize this solution, we will flip this and this gene from 0 to 1, and we get the optimized individual. Now, we can disturb the first gene, and then we can optimize it with the greedy genotype optimizer as well. And then we will flip, in the first iteration of this, we will flip this 0 to 1. Then, in the second iteration of the greedy optimization, we will flip this 0 to 1 too, as well. And finally, we will flip, in the third iteration, we will flip this 0 to 1. And we will get such an individual. And if we compare the results of this optimization, we will see that PLO will tell us that the first, fourth, seventh, and eighth genes are dependent, which is true, but the FreeLO will not report only the direct linkage, but will report more, and we don't want it. So the conclusion out of this is that, unfortunately, FreeLO cannot support only direct linkage. So the objectives of this paper are as follows. Of course, FreeLO supports only the true linkage, but we want to make another step, and we want to get only direct linkage. And the second objective is that FreeLO is too slow for being used by the SLL using EAs. So the objective is to propose such empirical linkage learning technique that is applicable to SLL using EAs. So we propose the direct linkage discovery, DLED. The idea is actually similar to FreeLO, but we only use the optimization procedure for a single pair of genes, and no greedy optimization of the whole genotype is done. So the effect is that DLED is significantly faster than FreeLO, and what is even more important is that DLED discovers only the direct linkage and nothing more. How it works? Let's consider such an individual. Now, we can disturb it and we get such individual. And if we compare the optimization only of a single gene here, then this gene will not change. On the other hand, here this gene will change to 1 because if we have 3 ones, we prefer to have 4 ones instead. And we can do this operation for all the pairs which are created by the fourth gene and the other part of the genotype. And what is the conclusion out of this is that then we can compare the results of this optimization. In this blue and red parts, the results differ. In this gray part, the results are the same. And you may take a look that the dependent genes will be only those which are directly dependent on gene number 4, because gene number 4 is a part of the red block and the blue block, and nothing more. So DLED is much faster than FreeLO, but it's still expensive. So the other idea behind which we present in the paper is to limit the fitness function evaluations number. And for each pair, we maintain the linkage discovery probability, which starts from value of 1. And when the new dependency is discovered, we reset all the probabilities for a given gene. And we also reset all the probabilities if we add a new subpopulation, or if in Eltigomia, or if population size in P3 is doubled. So here we have some results. The red line with a square, with a circle, is the Eltigomia. The purple line with a square is Eltigomia SLL. The red line is with DLED, and again P3 with DLED is blue line, and P3 with SLL, the original version, is the brown line. So you may see that for deceptive-free concatenations of the concatenation of deceptive functions, the SLL versions are faster, which is expected because for this kind of problems, SLL works very fast and very precise. Although you can still solve it, decompose this kind of problems with DLED. Again, for B model 10 noised deceptive function, you may see that DLED is significantly better here because SLL is unable to decompose such problems. Here we have some overlapping problems. For the cyclic problems, you may see that for the the DLED using versions are much faster and scale much better than the original ones. Here we have the Altigomia, this red and purple line, and the blue line and the brown are P3. So P3 with DLED and Altigomia with DLED work significantly better here. However, what is interesting is that for some overlapping problems like Ising-Spin glass or NK landscapes, of course, you may use P3 and Altigomia with DLED, but they work slower, sometimes more significantly, sometimes less significantly. We don't know why yet, but we are investigating this issue. However, some answer for this may be the DLED computation costs, which seem still quite high with respect of the whole run. So DLED is still expensive. However, it's cheap enough to be used by P3 and Altigomia. And for some overlapping problems, it works better. We don't know why SLL works better for some overlapping problems. We'll check it in the future. What is also interesting here is that for P3, you have the significant differences in fitness function evaluation number cost of DLED and the computation time cost of DLED. It's caused by the fitness caching, which is described in more details in this paper. So the conclusions. The objectives of the paper are met. We have proposed a DLED which detects only the direct linkage, and this is a kind of a next step in linkage learning precision. We have also proposed an empirical linkage learning technique which is fast enough for those optimizers which were originally proposed with statistical linkage learning techniques. The main future work directions are the investigation of problems with the overlapping structure and answering why statistical linkage learning is better for some of them, and new utilization ways of DLED. Thank you very much for your attention.